Welcome to the MOOCs course Transport Phenomena of Non-Newtonian Fluids. The title of this lecture is Viscoelastic Non-Newtonian Fluids. In previous couple of lectures what we have seen different characteristics of Newtonian fluids, and based on those characteristics we have defined non-Newtonian fluids, and then we have classified non-Newtonian fluids. We have seen these non-Newtonian fluids are grouped as time independent non-Newtonian fluids, time dependent non-Newtonian fluids, and viscoelastic non-Newtonian fluids. So, we have already seen enough details about the time independent and time dependent non-Newtonian fluids, their models, and then a few example problems as well. In the previous lecture we have also seen a few details about viscoelastic fluids. Now, in this lecture we will be discussing in detail about viscoelastic fluids once again, along with a few possible mathematical models that are well known for the case of viscoelastic non-Newtonian fluids. Viscoelastic fluid behavior, as the word viscoelastic indicates, these fluids will have both viscous as well as elastic behavior. Under certain limiting conditions, the elastic behavior may be predominating, whereas under some other conditions or some other range of shear rate, the viscous effect may be more important, right. But given a same material may be having both elastic and then viscous behavior, then such fluids are known as the viscoelastic fluids. So, what is elastic body? Perfect elastic body, it regains its original form on removal of applied stress. When we apply external force to elastic material, what will happen? It undergoes certain kind of deformation. However, when you remove the applied force, what will happen? The material will try to gain its initial position. If it is perfectly elastic, then it will come back to its initial position, otherwise it can only get back partially to its previous state. Okay. So, such materials are elastic materials. If completely they are coming back to initial position, then they are perfectly elastic solid materials. However, in the case of Newtonian viscous fluids, what happens? Shear stress is proportional to the shear rate, where the applied force, when you remove, the material will never come back to its initial position. It cannot even partially get back to its previous state. Okay. So, such materials, for such viscous Newtonian fluids, the shear stress is proportional to the shear rate. However, some materials have found to be display both elastic and then viscous effects, and are known as these, and these materials are known as the viscoelastic materials. Some textbooks you may also find the word elastico-viscous materials as well. Both of them are same indeed in general, but some people refer these materials as elastico-viscous material if the elastic behavior of the material is more compared to the viscous behavior. Okay. Otherwise, they are same. One can use either viscoelastic or elastico-viscous term for these materials. Obviously, what we can understand, two limits of viscoelastic materials are possible, and these are perfectly elastic deformation, one limit, and another limit is perfectly viscous flow. Also, this material may behave like a viscous fluid on one situation and may behave like elastic solid in another situation. That is also quite possible. That is what is one of the main characteristics of this viscoelastic fluid behavior. So, viscoelastic materials, thus they have ability to store and recover shear energy. Okay. So, that is basically about viscoelastic fluid behavior. We are not just talking about viscoelastic material, but we are in general trying to have a kind of more information about viscoelastic fluid behavior. So, we see a few examples or real life situation where you can realize this viscoelastic behavior in a given fluid. Okay. So, we start with couple of examples and then we go into the other details of mathematical details of representing this viscoelastic fluid behavior, etc. So, some proprietary soups they do have a elastic behavior, viscoelastic nature. How we can realize? Let us say you have a soup ball and then you are rotating with a stirrer. So, then what you can see these circles or internal circulations kind of things are possible. They are forming like this if your rotation direction is this one, right. So, but sometimes what happens, when you rotate it for some time, and then what you do, you stop rotating. Then what you can see that material, whatever the viscous fluid that you have taken or the soup that you have taken, that may be found like halting, or the internal circulations are found to be halting, and then they try to come back to previous locations or previous positions. That means rotations, the winding, whatever the internal circulation that you can see on the surface, they will move in the other direction, because after stopping the rotation, what happens, they try to go to the backwards, circulation may go in a reverse direction. Why? Because this material, whatever is there, if it is having viscoelastic behavior, then only it is happening, and then because of that elastic nature, the material remembers its previous position, and then it try to come back, right. So, it partially come back because it is also having the viscous behavior. So, then partial recovery is possible for the kind of viscoelastic fluid behavior. This is what one can realize easily in some of the situations, experimental situations, okay, where you can realize the elastic behavior a fluid if having, or let us say the soup is having elastic behavior. So, then you can have such rewinding of internal circulations is possible. It is not necessary that all the soups are having elastic behavior, viscoelastic behavior, only some of them are having viscoelastic behavior. So, you can try doing this experiment yourself at home or in restaurant, and then you may observe this kind of observation in general, and then you may observe it only if that particular given soup solution is having viscoelastic behavior, otherwise not, right. Only a few of proprietary soups are having this viscoelastic behavior, but not all the soups. Now, we take another example, rod climbing effect, which is also known as the Weissenberg effect, right. So, you take a solution of a polyisobutylene in polybutene, right. So, then now you take this solution in a ball, and then you try to rotate. You have a kind of a stirrer, and then that stirrer you are trying to rotate so that to mix the solution. What happens? So, in general, the fluid surface, when you are rotating, then you can see concave, this kind of surfaces in general you see if you rotate any kind of material that you take, right. If it is not having viscous behavior, when you rotate, the initial surface was like dotted line, let us say, but when on rotation, the top surface of the liquid will be drop like this, right, concave upward direction like this, okay. So, but now if the material is having any elastic behavior, it will try to climb the rod like this, it will try to climb the stirring rod like this. So, this is what known as the rod climbing effect, right. Why does it happen? Because when such material when such materials which are having elastic behavior also along with the viscous behavior, or for viscoelastic behavior, when you rotate, these rotations produces a stress which is perpendicular to the direction of the shearing, right. Because of that stress perpendicular to the direction of shearing, so a kind of normal stress would be developed, and then that normal stress leads this material to climb the rod like this, right. So, rather having kind of the surface like this, if it is having elastic behavior, the material will try to climb like this, okay. So, because the rotation, the shearing direction in the perpendicular to the shearing direction, stress would be developed, that is known as the normal stress. Because of that normal stress, the material tries to climb the surface like this. Another effect, dye swelling effect we can have. So, let us say you have a container in which you have a dye, and then you try to open it or take it through the outlet. So, what happened, it rather have falling down straight away like this in general, which you find for normal viscous fluids, right. So, it is showing some kind of swelling effect. What kind of swelling effect it is showing? You know, it swells like this at the outlet and then expands like this slightly and then falls out, rather than a kind of a straight path out like red color lines. Blue color lines indicate some slightly, it is swelling kind of thing. This swelling is also because of the stresses that are developed in a direction normal to the in a direction perpendicular to the shearing direction or normal to the shearing direction. So, here again we can see the normal stress are playing the role. Okay. So, now recollecting one of the characteristics of Newtonian fluid. Newtonian fluids, what we have seen, we see only shearing stress are possible, shear stress are only possible, normal stresses either identically 0 or their differences are 0, that is what we have seen. But in non-Newtonian fluids, those normal stresses may not be 0. Indeed, in the viscoelastic fluids, those normal stresses or their difference are not 0, okay, or unequal normal stress differences are possible. Unequal normal stress difference is possible in the case of viscoelastic fluids. So, that is the reason now we see a few details about normal stresses. So, normal stresses in steady shearing flow. Now, 1D shearing motion of a viscoelastic fluid we are considering. We have a fluid element like this here, confined between two planes. Now, we are shearing this plane such a way that shearing action takes place. This fluid element undergo shearing action. So, if it is only a viscous material which is not having elastic fluid, so then what we have seen, only stress developed, that will be shearing stress, and then that shearing stress would be in the direction of the shearing, and then plane on which it is working, that plane would be normal to the shearing direction. So, tau yx, because we are shearing in x direction and then in the other y direction only the velocity is changing. So, Vx velocity component is there and then that is function of y. So, then tau yx, that is the only stress is possible, because Vy, Vz are 0 here, that is how the limiting condition we are taking it, okay. Such a way that we are designing this experiment, shearing experiment, okay. But if this material, whatever the fluid element that you have taken, if it is not simply viscous fluid element, but it is a viscoelastic fluid element, then what happen, in addition to the shearing stress, you will also experience normal stresses. Pxx, Pyy, Pzz normal stresses are also possible. They are also possible. Indeed, because of that, those normal stresses only, so called rod climbing or die swelling effects that we have seen in previous slides, they are possible because of existence of these normal stresses. If the material simple Newtonian fluid, you would get only tau yx, okay. Simple viscous fluid, you will get only tau yx, you would not get any other kind of other normal stresses. You will be having those values only if the material is viscoelastic. So, in addition to the shear stress tau yx, you will also have 3 normal stresses, that is Pxx, Pyy, Pzz. These are also represented as sigma xx, sigma yy and then sigma zz in some books, okay. And then these normal stresses whatever are there, they are comprising 2 components, isotropic pressure and then contribution due to the flow or the viscous normal stress, okay. This normal stress is having isotropic pressure as well as the viscous normal stress, that is nothing but contribution due to the flow, right. So, how do we define them? Sigma xx is minus p plus tau xx. What does mean by minus p plus tau xx? These are acting in, though both of them are in a normal direction, but in a different they are opposite to each other, okay. So, let us say the pressure is acting towards the fluid surface, towards the fluid element that you have taken, whereas the viscous stress because of the flow is there, viscous normal stress because of the flow, that is acting towards the outwards the fluid element whatever we have taken. Okay, that is what this minus p and then plus tau xx. So, similarly sigma yy, sigma zz also you can write like this. So, this p indicate the isotropic pressure, whereas the tau xx, tau yy, tau zz are known as the deviatoric normal stresses if the viscous component is having only Newtonian fluid behavior. That is, if the tau versus gamma dot is linear behavior, then whatever this pressure, whatever this tau xx, tau yy, tau zz that are existing because of the elastic behavior, elastic part, they are known as the deviatoric normal stresses for Newtonian fluids. Okay. However, for this for non-Newtonian fluids, these are regarded as extra stresses. These are regarded as extra stresses. So, indirectly in the case of Newtonian fluids, what we have, this tau xx is 0, tau yy is 0, tau zz is 0, identically they are 0 or their difference is 0. So, when they are identically 0, how pressure can be defined? If you add them together, you will get minus 3 P is equals to sigma xx plus sigma yy plus sigma zz. That means isotropic pressure for the case of Newtonian fluid, you can define it as minus 1 by 3 sigma xx plus sigma yy plus sigma zz, right. But such kind of definition for the isotropic pressure is not possible in the case of non-Newtonian fluids. In the case of non-Newtonian fluids, having such kind of definition for this isotropic pressure is not possible, because for such kind of materials, whatever the tau xx, tau yy, tau zz are, the differences are not identically equal to 0. They are unequal, right. For non-Newtonian fluids, differences of normal stresses are measured readily than individual stresses. So, then we will be seeing in the subsequent weeks, where we will be measuring this rheological behavior, tau versus gamma dot, or tau yx versus gamma dot yx, etc. Those information, shear, that is indirectly shear stress versus shear rate information, etc. We are going to measure, we are going to see the working principles how to measure such a rheological behavior. In addition to them, we will also see the methods how to measure the normal stresses or normal stress differences. So, there we can see these normal stress differences whatever are there, they can be easily measured rather than the individual normal stresses like sigma x, like tau xx, tau yy. So, you can easily measure these differences rather than individual normal stresses. And then whatever the rod climbing effect due to the Weissenberg was seen in one of the previous slides. So, probably that is the first one to have a kind of information that the shearing motion of a viscoelastic fluid gives rise to unequal normal stresses, So, when you are defining shearing motion or shearing flow of a Newtonian fluid, or a fluid which is not having any elastic behavior, so then what you need to you need to have simply tau versus gamma dot information is only required, right. Only tau versus gamma dot information is only required, but if you wanted to define a shearing flow of viscoelastic fluids, in addition to this tau yx versus gamma dot yx, you also need to have a n1 versus gamma dot yx and n2 versus gamma dot yx, that information is also required, or n1 is nothing but first normal stress difference and then n2 is nothing but second normal stress difference. So, in addition to the shear stress versus shear rate information, you also need to have information about the first normal stress differences versus shear rate and second normal stress difference versus shear rate information also, in order to completely define rheological behavior of viscoelastic material, right. So, now this N1, N2 we see a few more details now. Some examples if you see. So, let us say I have taken polystyrene in toluene solution. So, the first normal stress difference N1 is plotted against the shear rate. So, you can see there for different weight percent of a polystyrene in toluene solution, you can see different curves like this are possible. Now, their shapes are also changing, they are not having, they are appear to be similar, but they are significantly different from other, that is what you can see. And then also tau versus gamma dot, whatever the curves that rheological curves that you have seen for time independent or time dependent non-Newtonian fluids, they are having a particular shape, right. The shape, the size, etc. are maybe changing, but they are having, for a given type of material, they are having particular shape. So, but for viscoelastic fluids, it is not necessary that you may get all these kind of shapes only for all the fluids. Okay. Right. So, this is the first normal stress difference, and then under the limiting conditions of low shear rates. Under the limiting conditions of low shear rate, what we can see, this data whatever is there N1 versus gamma dot, you can see a kind of approach. You can see there we can draw a kind of straight line of slope 2, that is what we can see. Okay. So, because of this region only, in general viscosity, when you define viscosity, you define, or apparent viscosity, you define what you do, shear stress divided by shear rate only, simply you do. But similar stress coefficients like viscosity that we have defined, likewise using the normal stress differences, if you wanted to define the stress coefficients that we are going to do in next slides, they are, let us say, psi 1, psi 2 like this they are given. So, there you will be seeing this psi 1 is N1 by gamma dot Yx square, because under the limiting condition of low shear rate, N1 is expected to have a proportionality behavior with respect to the square of the shear rate, but not individual shear rate. Okay, that is the reason you can see N1 is proportional to the square of shear rate at low shear rates, that is what we can see from this graph. Okay. So, second normal stress differences, you can see the negative of second normal stress difference is shown here. So, that is having different nature depending on different weight percent of the polystyrene toluene solution. Just in order to have a kind of feel about their normal stress differences, I have shown these graphs. Okay. Now, the normal stress coefficients, they are defined as first normal stress coefficient, N1 is the first normal stress difference, psi 1 is the first normal stress coefficient, right. So, that is N1 by gamma dot Yx square, y square, because previous slide we have seen the stresses at low shear rate are having a kind of limiting nature, that N1 proportional to gamma dot Yx square. Okay. So, similarly, second stress coefficient psi 2 is N2 by gamma dot Yx square. So, now the units, if you see, you can have Pascal second square from here, because gamma dot is having second inverse. So, the stress differences are having Pascal. So, Pascal by 1 by second square. So, then Pascal second square you will be getting, right. Whereas, the apparent viscosity, the viscosity whatever we have seen before the viscoelastic materials, they are having units of Pascal seconds, because there whatever this apparent viscosity is there. So, we simply had tau Yx by gamma dot Yx, not the square of gamma dot Yx. Okay. So, that is the reason this difference is there. And then rate of decrease of psi with shear rate is greater than that of apparent viscosity. This is another experimental observation. And then, as we have already seen, at low shear rates, N1 is expected to be proportional to the square of shear rate. So, obviously, this psi 1 tends to a constant value of psi naught at low shear rates. This is valid only at low shear rates region, not for all the ranges of shear rates. So, further this N1 by tau is found to be a measure of degree of elastic behavior of liquid, because this N1 is the first normal stress difference which comes into the picture if the material is having elastic behavior only. So, that divided by the shear rate whatever is there, it gives the relative contribution of these two. So, that means what we can understand with respect to the shear rate, whatever N1 by tau information is there, that gives the degree of elastic behavior of a liquid. So, this N1 by tau, if it is very small, tends to 0, that means we can say that the elastic behavior is negligible, or the material is not having elastic behavior, it is only having the viscous behavior. If this N1 by tau is tends to infinite or large values, then we can say that material is having large elasticity, or highly elastic behavior is having, that is what we see. However, rather N1 by tau, it is N1 by 2 tau which is called as a kind of a recoverable shear. Okay. And then this value greater than 0.5 is also possible, and then it is not at all uncommon. Having n by 2 tau greater than 0.5 is not at all uncommon, but however we call them are highly elastic in nature. N1 information, N1 versus gamma dot Yx information whatever is there, that is very much lesser information compared to the tau versus gamma dot information. Whereas N2 versus gamma dot information, even lesser information is available because of the limited studies have been carried out. Sometimes it is also found that N2 is order of magnitude smaller than N1, and even it is negative, as we have seen as one example, N2 negative of N2 versus gamma dot shear rate that we have seen. Sometimes it is also found that N2 may also change the sign, such kind of examples are also found. So, these are a few basic details about this viscoelastic materials. So, now what we see? We see mathematical models for viscoelastic behavior, right. So, mathematical models, when we talk about mathematical models for a given material, so we need to have a components which represent true physics or physical behavior of the material. So, now here what we have in this viscoelastic material, we have both elastic and then viscous nature. So, then we have to have a component which represent the elastic behavior mathematically, and which also have a component which mathematically represent the viscous behavior of the material. So, viscoelastic fluids display fluid like and solid like characteristics simultaneously, that we already know. So, thus mathematical models of these fluids hinge on linear combination of elastic and then viscous component. So, linear combination, nowadays non-linear combinations have also been found, and then several different types of viscoelastic fluid behavior models are available, but we take a few cases, a couple of cases only, where we have a linear combination of elastic and then viscous components. These linear combinations again we can have them in series and parallel. So, accordingly we have two models, we are going to see these two parallel we are going to see these two linear viscoelastic fluid models. So, analogously mechanical representation of this material we can have like a springs, representing elastic components, and then dashpots representing the viscous actions. So, when we have these two in series, then we call that model Maxwell model, and it is perhaps the cornerstone of the linear viscoelastic models, and then it does capture salient features, though it is a crude model. So, now first we see this Maxwell model, where we have the linear combination of viscous nature as well as the elastic nature represented by dashpot and elastic component, spring component, okay, respectively. So, Maxwell model, mechanical analog of this model is a series combination of spring and dashpot, right. So, they are arranged in a series like this. So, Now we have a spring here whose Young's modulus is G, and then we have taken a dashpot, so which is a vessel containing a Newtonian fluid. To the outlet of this container we have a flow constrictions, so that whatever the delta P versus flow rate information is there, they are proportional. Okay, delta P pressure drop is proportional to the volumetric flow rate. Such kind of flow constrictions are there. So the viscosity of the Newtonian fluid is mu, that we have taken in this vessel, which we are now taking as a kind of representation of viscous behavior as a dashpot, and then we are taking a spring to have a kind of elastic component, elastic behavior. So now when you apply certain force to this top position here, so that will go to the spring, and then because of the movement in the spring, whatever the piston that is connected to the spring, that is inserted into this vessel. So because of this piston, the deformation in the Newtonian fluid will take place. Okay. So now whatever the strain rate are there, so they are different in each of them, they are not equal, because it is passing first through the spring, then it is coming to the viscous fluid. Okay. So then whatever strain in the spring is there, let us say if you take gamma 1, whatever the strain in the dashpot is there, so that if you take a gamma 2, right. So then the total strain whatever is there would be the summation of these two. That makes a basis for this model, and then subsequent mathematical simplification takes place. So now individual strain rates gamma 1 dot and gamma 2 dot, strains are gamma 1 and gamma 2 respectively, strain rates are gamma 1 dot and gamma 2 dot for these two components. So total strain rate would be nothing but gamma dot is equals to gamma 1 dot plus gamma 2 dot. Gamma 1 dot we are writing d gamma 1 by dt, and then gamma 2 dot we are writing d gamma 2 by dt. Now either side what we do, we first multiply by viscosity mu. So mu gamma dot is equals to mu d gamma 1 by dt plus mu d gamma 2 by dt. Next step, what we are going to do, to this elastic component we are dividing and then multiplying by Young's modulus, so that mu by g multiplied by g d gamma 1 by dt, we can have one term, and then this mu by g is nothing but relaxation time, which is the characteristics of the material, which is the characteristic of the viscoelastic fluid. Okay. Plus second term mu d gamma 2 by dt is as it is, right. So now Hooke's law what we have tau is equals to minus g dx by dy. This dx by dy is nothing but gamma 1. So tau is equals to g gamma 1 according to Hooke's law, right. Now if you take a differentiation either side with respect to time, so we have d tau by dt is equals to g d gamma 1 by dt. So that in place of here, wherever you have a g d gamma 1 by dt, you can simply write d tau by dt. So we have left hand side mu gamma dot as it is, right hand side first term is lambda multiplied by d tau by dt plus tau. This is what we are having. This is the primary equation for the Maxwell model. Now this equation you can solve for different lambda values and then see the behavior of this material with respect to the time. So at constant strain rate, so that means when gamma dot is equals to 0, when gamma dot is equals to 0, that is d gamma by dt is equals to 0. So in the previous equation whatever that we have, this equation mu gamma dot is equals to lambda d tau by dt plus tau, this what we have. So if the at constant strain rate, that is gamma dot is equals to 0, or at constant strain rather than rate, at constant strain what we have, this gamma is constant. So, then gamma dot should be 0. So, d gamma by dt is equals to 0. So, then tau plus lambda d tau by dt is equals to 0, that we can have a simply d tau by dt is equals to minus tau by lambda. So, now you can integrate this equation and then apply at t is equals to 0 whatever the stress is there. So, that is the maximum, whatever the stress at t is equals to 0 is there, that is the maximum, because that is gradually decaying as the spring is moving up and down. So, the piston connected to that spring is dissipating that stress to the Newtonian fluid that has been taken in the vessel as a dash part. So, that is gradually decaying. So, that is what physically also we understand. So, at initial time t is equals to 0, the stress has to be maximum for this model. So, then when you integrate this equation and then apply this boundary condition, you will get simply tau is equals to tau m exponential of minus t by lambda, right. So, here when rapid strain is applied and thereafter maintained at this value to this maximum fluid, this above equation what indicates? It indicates the stress, whatever the tau is there, that stress decreases with time, or decay of stress with time. That is what we can see from this equation, right. So, graphically also we are going to see this behavior of this particular equation now. So, now just now we derived for Maxwell for viscoelastic fluid, whatever the Maxwell model is there, that we have tau is equals to tau m exponential of minus t by lambda, right. Now, when t is equals to 0, exponential of minus t by lambda is equals to exponential of 0. So, whatever this exponential term is there, that is equals to 1. That means tau is equals to tau m, that is response is simply that of spring alone, the elastic fluid nature is only showing, because this whatever the t by lambda can be 0 for two cases, when t is equals to 0 or when lambda is equals to infinity. So, lambda is infinity, that means purely elastic behavior. Lambda indicates the relaxation time of the material, which is the characteristic property of the viscoelastic material. If it is large, that means elastic nature is very large for that material. Like lambda is like a property of the material, like density, the viscosity, thermal conductivity, etc. We are having physical properties. Like similarly, one of the rheological property of this viscoelastic material is this relaxation time lambda. Okay, it does not change with the condition, it is the material property that we are having. So, at t is equals to lambda, if you do the same thing, exponential of minus t by lambda would be nothing but exponential of minus 1. So, then what we have? We have tau is equals to tau m by epsilon, that is stress dropped from tau m to tau m by E value as the time progresses from t is equals to 0 to t is equals to lambda. So, now from here what you have, tau by tau m is equals to 1 when lambda tends to infinity or t is equals to or t tends to 0. This is what we have. So, pictorially if we have, so here whatever the lambda is there, that indicates rate of stress relaxation. So, pictorially if you see, when lambda is very large, lambda tends to infinity, that means exponential of whatever minus t by lambda is there, that is exponential of 0. So, that is 1. So, then tau by tau m should be equals to 1, because now this we are plotting not tau versus t, but we are plotting tau by tau m versus t. So, when lambda tends to infinity, that is material is fully elastic, perfectly elastic response is there. So, then tau by tau m would be having this line like this. But as the lambda value decreases, the elastic responses gradually decreases and the viscous response gradually increases, right. And then at certain position what we have a kind of perfectly elastic, perfectly viscous behavior when lambda tends to 0, right. So, as lambda decreases, you can whatever the tau by tau m is equals to 1 is there. So, that will start showing this kind of behavior for decreasing lambda values with respect to time. With respect to time, tau by tau m may be having this kind of behavior as shown here, tau by tau m versus may have this kind of behavior for different lambda values. Lambda tends to infinity, we have this nature. When lambda decreases, so then you have this kind of curves like this, whatever drawn here like this. Further, when lambda equals to 1, you can have this behavior. When lambda is equals to 0.5, you can have this behavior, right. So what we can see, when lambda is decreasing, viscous behavior is increasing. When lambda is increasing, elastic behavior is increasing for that material. So, lambda is a kind of a characteristic of a material, so which indicates the how strongly elastic nature that material is having. If it is large value, then it is a highly elastic material. So, now we see Kelvin-Voigt model, which is the other model where we have the linear combination of again spring and dashpot, but now these are parallel to each other. So, now we have a spring whose strain rate whose strain is gamma 1, and then whatever the strain in the viscous fluid or the container having viscous Newtonian fluid, the strain is gamma 2, right. So, now again here also the material, whatever the Newtonian fluid is there, that is taken, or the Newtonian part, viscous part is there, that is taken in this container, which is again at the bottom is having the flow constriction with the pressure drop is proportional to the volumetric flow rate. So, now what happens here when you apply external force at the top, so then whatever the strain rate is there, that is going to be same for both of the components because it is equally transmitted, but the stresses are different. So, the stresses are added together in general to get the total stress, right. Whereas in the Maxwell model, the strain rates are different, stresses are same. So, then we added the strain rates together to get the total strain rate. So, that is the difference between these two models. So, in this arrangement in this parallel arrangement, whatever the strain rate in two components is there, that is equal. So, thus stress strain relation of this system obtained by adding individual stresses in two elements. So, that is tau is equals to G gamma plus mu gamma dot, right. So, now again what we can do, we can write this gamma one side, so that tau by G minus mu by G gamma dot we can have the other side. This equation, what I am trying to do, I am writing tau minus mu gamma dot first, tau minus mu gamma dot is equals to G gamma. So, gamma is equals to tau by G minus mu by G gamma dot, and then this mu by G we can write it as lambda. So, that this equation gamma is equals to tau by G minus lambda gamma dot, we can write this lambda is nothing but again relaxation time of the viscoelastic fluid, relaxation time of the viscoelastic fluid. So, if the stress is constant at tau naught and initial strain is 0, then what we can see, upon removal of stress, the strain decays exponentially with the time constant lambda mu by G. In the previous case Maxwell model, what we have, stress decays exponentially from tau m to tau m by E as time progresses from t is equals to 0, t is equals to lambda, right. But here the strain decays exponentially with a time constant lambda is equals to mu by G. That is what difference between these two models. So, by comparison, Maxwell model has a predominant feature of more fluid like response, whereas the Kelvin-Voigt model has feature of solid like behavior, because this material does not exhibit unlimited non-recoverable viscous flow. Further, it will come to rest when the spring has taken up the load. So, this Kelvin-Voigt model has a feature of more solid-like behavior, whereas the Maxwell model having the feature of more fluid-like response. Now, the dimensional considerations for viscoelastic fluids we see. Two different possibilities we see under the dimensional consideration for viscoelastic fluids. So, first one is the Maxwellian relaxation time. So, whatever the relaxation time lambda is there, so can we have a kind of a dimensionless relaxation time. So, that is the point in a basic in one single word, if you want, single line if you wanted to say, if one single line if you wanted to say whatever the relaxation time lambda is there. So, can we have a kind of dimensionless representation of the same time constant or relaxation time. So, first we see the Maxwellian relaxation time. So, there are several ways of defining a characteristic time by combining shear stress and first normal stress differences. Okay. So, Maxwellian relaxation time is taken that information into the consideration that whatever the n1 versus gamma dot yx information is there, similarly whatever the tau yx versus gamma dot yx information is there, that has been taken under consideration such a way that we can have this lambda f is equals to n1 by 2 tau yx gamma dot yx, which is known as the Maxwellian relaxation time, which is known as the Maxwellian relaxation time. So, however, in the limits of 0 shear rate or the low shear rates, what we know, this psi 1 and then mu both approaches a constant value. Psi 1 approaches psi naught and then mu approaches whatever the mu naught. Okay. Psi 1 approaches constant value psi naught and then mu approaches 0 shear viscosity mu naught. So, both of them are constant, that we have already seen. So, obviously, if these two are under gamma dot yx tends to 0, if these two are having limiting constant values, so then whatever the lambda f defined based on that information, that will also have a constant limiting value. However, practical utility of lambda f is severely limited, as in most applications shear rate is not known a priori. So, if you wanted to know this one, you have to know what is this gamma dot yx and all that for a given application, then only you can use it. So, in order to overcome, there are different ways of defining relaxation time, dimensionless relaxation time have been carried out, and one of that representation is lambda f is equals to m1 by 2m whole power 1 by p1 minus n, that is what we have. And then it is based on assumption that both n1 and shear stress approximated by power law functions of shear rate. So, that is n1, this is the assumption in defining this particular alternative relaxation time lambda f. Alternative dimensionless relaxation time lambda f is represented by this way. Right. So, in order to define this one, these are the two assumptions have been taken. What are these assumptions? That normal stress, first normal stress differences versus shear rate. So, whatever the first normal stress difference versus shear rate, and then shear stress versus shear rate information, whatever there experimentally obtained information is there, they are represented by some power law model like this. Right. Then they obtain this one. So, however, thus there is no necessity to extend rheological measurements to 0 shear rate region if you are using this equation, Okay. But in the limit of 0 shear rate, P1 tends to 2 and then N1 and N tends to 1, this above equation whatever is there, that will again get back to our Maxwellian relaxation time of lambda f is equals to N1 by 2 gamma dot yx tau yx, this is what you get. How? Let us say from this equation n1 information, if p1 is equals to 2 if P1 is equals to 2, then square root of N1 is equals to square root of M1 is equals to gamma dot Yx. That means M1 is nothing but N1 by gamma dot Yx square, this we already know. And then similarly, when n is equals to 1, then we know m is equals to tau Yx by gamma dot Yx. If you substitute this m1 and then m here under the limiting conditions, then we have lambda f is equals to m1 is n1 divided by gamma dot Yx square 2, and then m is nothing but tau Yx by gamma dot Yx. So, that is nothing but, because whole power 1 by P1 minus n, P1 is 2, n is 1. So, that power is 1. So, then what we have, n1 divided by 2 gamma dot Yx tau Yx, this is what having. So, which is same as, which is nothing but Maxwellian relaxation time. So, this is better way. What is the difference between that equation number 1 and 2, that two different forms of Maxwellian relaxation time is that if you use this one, you do not need to extend the rheological behavior to 0 shear rate region. So, another dimensional consideration for a viscoelastic fluid behavior we take in the form of Deborah number. What it is, that is what we are going to see. So, in general, for Newtonian fluids, the state of flow we can describe by two dimensionless numbers. One is the Reynolds number, another one is the Froude number. Reynolds number is nothing but ratio between inertial force to the viscous force. The Reynolds number is nothing but the ratio between inertial force and viscous force, whereas the Froude number is nothing but ratio between inertial force and gravitational force. So, these two are known. So, then you can define the state of a flow for a given Newtonian fluid. Okay. So, for viscoelastic fluids as well, at least one additional group involving elastic effects is required. So, that is what we call Deborah number. So, this Deborah number is nothing but the ratio between relaxation time and deformation time. This relaxation time is nothing but the material characteristic. It is the material characteristic. Deformation time is depends on the flow situation. Right. So, if in the obviously, so relaxation time also, that is indicates if it is large, so then obviously its elastic behavior is more significant. That is what we can see, that is what we understand. So, if it is this Deborah number is very large, so then it represent highly elastic behavior in the flow system, right. If it is very small, so that means we can say that so called viscous effects, so called elastic effects are having less influence on the flow situations. So, greater the value of Deborah number, more likely the elasticity to be of practical significance in that flow situation. Why flow situation? Because the deformation time depends on the flow situation, right. So, that we take one example and then realize quickly. So, if Deborah tends to 0, Deborah number tends to 0, we can say more viscous effects are dominant. If Deborah tends to infinity, we can say that elastic behavior is dominant. So, now we see couple of problems to conclude viscoelastic fluid behavior. Okay. So, so and so fluid rheological behavior has been measured, and then that is given shear stress versus shear rate information, and then first normal stress difference versus shear rate information is given. Shear rate is changing from 0.05 to 9.97, that is almost 0 to 10 second inverse. Okay. When shear rate is in this range, so corresponding shear stress and then first normal stresses are given here. First normal stress differences are given here. So, the first part of the question, does this fluid exhibit Newtonian or shear thinning fluid behavior? If you wanted to know Newtonian or shear thinning behavior, what you have to do? You have to plot tau versus gamma dot, right. If it is passing through origin and linear, it is Newtonian behavior. if it is passing through origin, but it is not linear, then we can have either shear thinning or shear thickening behavior. Okay, so that we can see. Second part of the question, is the liquid viscoelastic? Obviously it is viscoelastic because first normal stress difference is given here, right. So we can see the Maxwellian relaxation time and then N1 by 2 tau calculations also we can see, because we know that N1 by 2 tau indicates the recoverable shear for the case of viscoelastic fluids, right. So then we also need to do Maxwellian relaxation time versus shear rate plotting. So the same information plotted here. So this shear stress versus shear rate, and then first normal stress difference versus shear rate is given. So Maxwellian relaxation time, that is lambda f is equals to N1 by 2 tau yx gamma dot yx information that you have when you do it. So then you get these values, right. And then we also wanted to know whether this material is having sufficiently elasticity or not. So then N1 by 2 tau calculation we have to do. When we do these things, we can see N1 by 2 tau is having more than 0.5 also. If it is more than 0.5, we have already seen that material is having highly elastic behavior, and then that elastic behavior is showing more significance when the shear rate is larger. When shear rate goes 8 or higher, so then we can see N1 by 2 tau is going more than 0.5 values. That means the elastic behavior is having large influence on the flow situations. So coming to the rheology of Newtonian or shear thinning behavior to know. So the shear stress tau versus gamma dot yx is plotted here. So then we can see this curve, all these data points forming a straight line, providing the viscosity 2.9601 pascals, and then it is passing through the origin. So it is a Newtonian behavior, right. So we also asked to plot lambda f Maxwellian relaxation time versus shear rate. So then that you plot, so you can see this curve here. It is not 0, so then it is having significant value. So then elastic behavior, this material is also having elastic behavior. One last example problem on Deborah number. So consider a flow of 1% aqueous polyacryl amide solution having relaxation time of 10 milliseconds. So relaxation time is given. That is the characteristics of the material, that is like a property of the material. So this material is flowing under 3 different conditions. One condition is a packed bed of particle size 25 mm at a superficial velocity 0.25 meter per second. So Deborah number, if you wanted to know, you need to know this relaxation time divided by the deformation time. This deformation time is nothing but whatever the particle size is there, that divided by the velocity. If you do, you will get the so called deformation time. So then this overall this 10 milliseconds also you convert into the seconds. So then you will get the Deborah number. So you have to calculate Deborah number like this, and then accordingly you have to say whether the material, whether the viscous effect is important or not. So that is same is the second situation also. The same material is flowing through a packed bed of particle size 250 microns, but at a superficial velocity of 0.25 meter per second. And third case, in a free jet discharge with a velocity of 30 meter per second through a nozzle of 3 mm diameter. So for each of the case we have to find out the Deborah number and then explain the possibility of viscoelastic effects in these cases. So first case, deformation time is nothing but whatever the particle size 25 mm divided by velocity 0.25 meter per second. So you get 0.1 second, that is nothing but 100 milliseconds, alright. So then Deborah number would be relaxation time by deformation time. Relaxation time is 10 milliseconds divided by the deformation time is nothing but 100 milliseconds, just now we calculated. So it is 0.1. So it is very small value. So the elastic effects would be weak or small in this case, first case, where this material is flowing through packed bed of particle size 25 mm at a superficial velocity of 0.25 meter per second. Now, what is the physical importance of this calculation? So, though the material that you are processing is having elastic behavior, so your condition, your velocity, if you maintain less than 0.25 meter per second and then particle size is not less than 25 mm or more than 25 mm, you will have a situation like the elastic effects would be negligible. So, in your design equation for the packed bed, you do not need to consider so called elastic effects. You can straight away use the Ergun's equation or Koenig-Kármán equation depending on the flow situation, flow condition, and then get the pressure drop information and all that without worrying about the elastic behavior of this material. That is the physical importance of getting these numbers calculated. Now, similarly for the second case, deformation, you see it is 250 microns. So, 250 into 10 power minus 6 meters of particle size divided by 0.25 meter per second of the velocity. So, then you get 10 power minus 3 seconds. So, that means 1 milliseconds. So, now Deborah number relaxation time by deformation time, that is 10 by 1 is 10. So, that is it is neither small nor large nor very large. So, both viscous and then elastic effects would be important, both of them should be considered. So, then if you have the particle size something like 250 microns and then velocity like higher than the 0.25 meter per second, something like this, if are your flow conditions, in the design of packed bed you have to worry about incorporating the changes in the pressure drop relations because of elastic behavior, that should also be incorporated. Or if you cannot change the design already existing packed bed, so then you have to change your operating condition such a way that this Deborah number should come down, like increasing the particle size or decreasing the velocity, such kind of things you have to do, and then find out a combination where Deborah number is very small, so that you can avoid the elastic contribution in the overall flow situation. If you cannot do that one in the design, you have to incorporate the effect of elasticity for this packed bed case, for these flow conditions. So, both viscous and elastic effects should be considered for the first case. So, the last case 3 mm nozzle dia. So, 3 into 10 power minus 3 meters and then 30 meter per second is the velocity. So, 10 power minus 4 seconds, that is 0.1 milliseconds. So, now Deborah number would be relaxation time 10 divided by the deformation time 0.1, it is 100. So, it is very large value, it is very large value. So, that elastic effects would be very strong, you cannot avoid at any circumstances, you have to incorporate in the design also the elastic effects should be incorporated. You have to incorporate elastic effects as well in the design as well as the operational situations for this condition, third condition. Right, that is the point having these calculations. So, this is all about the viscoelastic fluid behavior, including the possible mathematical models and then example problems. So, the references for this lecture are given here. These two references are very essential for this viscoelastic fluid behavior, right. So, other references are also provided here, okay, as a kind of reference. Thank you.